Today, we're going to dive into the invisible forces that govern our world. I mean, everything from the crushing pressure at the bottom of the ocean to the delicate tension on the surface of a single drop of water. We're talking about the hidden world of fluids.
Okay, I know it sounds like the beginning of a really weird joke, but the answer connects all three of them. They are all ruled by the fascinating and sometimes pretty bizarre laws of fluid mechanics. By the end of this, you'll see exactly how. So, let's get into it.
All right, first things first. When you hear the word fluid, you probably picture water, right? And you're not wrong, but honestly, that's just scratching the surface. The real scientific definition is so much broader and way more interesting. To put it simply, if you try to push it sideways, that's what we call shear stress, it will flow. A solid, like a brick, will just sit there and resist. But a fluid, whether it's air, water, or even honey, it's going to start to move. And that one simple property, it's the key to literally everything else we're about to talk about. And this is where things get really cool. We tend to think that fluids just flow in a nice, predictable way. But so many of the fluids we use every single day completely break the standard rules, and often in some pretty spectacular ways.
Now, this chart might look a little complicated, but just think of it as a map of how different fluids behave when you put them under pressure. That vertical line, the shear stress, that's basically how hard you're pushing. The horizontal line is how fast it's flowing. See that straight line for a Newtonian fluid? That's your everyday water or oil. Super simple. The harder you push, the faster it flows. But all those other curves? Those are the rebels, the fluids that play by their own set of rules.
Take Bingham plastics, for example. This stuff acts like a solid until you apply a very specific amount of force. It just sits there, but the second you cross that line, it starts flowing. And the perfect example? Squeezing toothpaste out of a tube. It does not want to come out until you give it that initial push. Then you've got these guys, pseudoplastics, or what you might call shear thinning fluids. The more you stir them or agitate them, the less viscous, or you could say thinner, they get. Blood is the classic example of this. It's a property that actually helps it flow way more easily through the tiny little capillaries in your body. It's fluid dynamics engineering happening inside you right this second. Okay, now let's zoom way in. Let's go from the big picture of a fluid down to its very edge, because what happens right on the surface is this constant battle between molecules, a microscopic tug of war that has some very, very visible results. I mean, it seems like a total contradiction, doesn't it? How can the exact same liquid pull itself into a tight little ball on one surface, but then turn around and defy gravity to climb up another? Well, the answer is in two competing forces. And this slide shows those two outcomes perfectly. On the left, you've got water spreading out all over a surface in a process we call wetting. But then on the right, look at that mercury. It's pulling itself into a tight little ball, basically refusing to spread out. It all comes down to who wins that molecular tug of war. And here are our two fighters. First, you have cohesion. That's the force that makes a fluid's own molecules want to stick together. Then you have adhesion. That's the force that makes those same molecules want to stick to whatever surface they're touching. So here's the kicker. When the attraction to the surface, that's adhesion, is stronger than the attraction the liquid has to itself, that's cohesion, the liquid will literally start to climb the walls. That is exactly what's happening when a paper towel soaks up a spill. The water is just more attracted to the paper fibers than it is to itself. All right, let's scale back up. We're going from the microscopic surface to the immense, crushing forces that are exerted by the entire weight of a fluid. This is where we really start to feel the pressure.
This device is a barometer, and it's honestly one of the most elegant experiments in all of physics. It shows that the air all around us, the stuff that feels like nothing, it actually has weight and it exerts pressure. In fact, the weight of our atmosphere is strong enough to hold up an entire column of mercury. We are, for real, walking around at the bottom of an ocean of air.
Now, when we measure pressure, the reference point is everything. Absolute pressure is the total pressure measured from a perfect vacuum, from zero. But in our everyday lives, we almost always use gauge pressure. That's what you're using when you check your car tires. It's just the pressure above the surrounding atmospheric pressure. This right here, this is an absolute game changer from Blaise Pascal. It means that if you're underwater, the pressure isn't just pushing down on you. It's pushing on you from the bottom, from the sides, from every single direction, all with equal force. And this one simple fact is the foundation for everything from hydraulic lifts to, why things float. Which brings us to one of the biggest questions of all.
We just said pressure pushes in all directions. So how in the world does a massive steel battleship, weighing thousands and thousands of tons, stay on top of the water?
And we can all thank Archimedes for this one. This is the eureka moment. Any object in a fluid feels an upward push. It's called a buoyant force. And the strength of that push is exactly equal to the weight of the fluid that the object pushes out of the way. So a battleship floats because its huge hull displaces a massive amount of water, and the weight of that water is enough to push back and hold the entire ship up.
You can really see the battle in its simplest form right here. Gravity is pulling the object's weight down, the buoyant force is pushing it up. If buoyancy is greater than or equal to the weight, it floats. If the weight is greater, it sinks. Simple as that.
But just floating isn't enough, you also have to be stable. This is all about the location of two critical points, the center of gravity, where the weight acts, and the center of buoyancy, where that upward push is acting. For stable floating, you want your center of gravity to be below the center of buoyancy. That way, if the object gets tipped, the forces will actually create a little twist that rights it. If you get it wrong and gravity's too high up, it'll capsize.
So, we've covered the what, the why, and the how of static fluids. But how do we take all these principles and actually use them to design things like massive dams that have to withstand incredible pressure, or submarines that need to control their own buoyancy? Well, that's where theory meets reality. You don't build a full-size dam or a brand new submarine and just kind of hope for the best. You build a model. By understanding the physics of fluids, engineers can create small-scale replicas and then perform tests that will accurately predict how the full-size version, the prototype, is going to behave in the real world. And the advantages here are huge. I mean, it's obviously way cheaper and a whole lot safer. But more importantly, it lets engineers actually see these principles in action. They can model the immense pressure on a dam, test the stability and buoyancy of a new ship hull, and perfect a design before a single real-world part is ever built. This is how we take the fundamental laws of fluids and use them to shape our world.
So, from toothpaste to battleships to the blood running through our veins, we've seen that fluids are way more than just water. They're strange, they're powerful, and they are absolutely essential. They follow a specific set of rules that govern everything from a water droplet to a warship, which leaves us with a final thought. What other invisible fluid forces are secretly shaping our world right now? Thanks for watching.